Welcome back, AP Calculus AB. Today we're going to conclude our Logistic Differential Equation section. Hopefully you watched the video for the previous class because that gave you all the information about those logistic differential equations, the fact that we can either have growth or decay over here. Today we're just going to look at a few things that you actually have to be able to do on the AP exam. Now, don't stress too much because this topic is not the world's most common. All we're really looking for here is to get one extra question right. That's about the number of times this will show up on the AP exam. But if we're going to do something, we're going to do it right. So let's go through. What do we actually need to do on the AP exam? Well, one thing is you need to be comfortable with the general format of a logistic differential equation, right? That's realizing that our derivative, our dp dt here, is going to take the format of either this L minus P inside, and then we have our exponential growth, that's the Kp, or with L factored out, which would cause this inside to be a 1. So the example I have here, and you should try this without me, is which one is a logistical differential equation? And as you look through, we know that this has to be in terms of P for our answer, which immediately eliminates A and B. Looking at these other three, hopefully it's somewhat apparent that E is the one that matches the format. Nothing too much to do here. Okay? If you wanted to go further, you could identify 5,000 as your carrying capacity, and that would be pretty cool, but that's about it. The second thing you should be comfortable with doing is identifying the different pieces of a logistical differential equation. And those pieces are pretty easy to identify depending on how the problem is written. If the problem is written in this first format, which is why I prefer it, you can very easily see the value of K and see the value of L. However, sometimes it is written in our second format and those values become a little bit harder to take a look at. So let's take an example. We're going to try and identify the constant of proportionality, the value of K, and also the carrying capacity, the value of L. So, we look at this and we see this is P over 5, so maybe we can think of this as 1/5 P times 1 minus P over 12. Now the problem here is that this guy fits our second model. We know that by the 1 minus P divided by something. Well, on the plus side though, we know what L is. L is 12. But on the downside, it makes K a little bit harder to identify because K is rolled in with the L that's multiplying by P. So what I'm going to do is I'm going to say that we know L times K has to be equal to the 1/5 that's right here. And because we know what L is, right, we found that L is 12, now we have a quick little equation that we can use to solve for K. Dividing or multiplying by 1/12, we can see that K will be 1/60. So I think now that you have that down, why don't you try the other three? I will go through them, but I think you can probably finish them off faster than I can explain them, and then you can skip through the video to make sure you got it right. Once you've tried all three, you can come back together. Alright, we're on to part B. I think part B is actually a little bit easier than part A because we're already in our first form of our differential equation, which means that we can tell L is 6 because it's not 1 right there, pretty easy. And we can also see the value of K because it's just Kp on the outside, and so K has to be 2/3. Woo! As we continue through, we'll look at part C. Part C, unfortunately, again, fits that second format, so we'll do the same thing as before. We can at least identify L here. We can see that L is 7. And then we know that L times K has to equal the 0.6 that's out front. I'm actually going to write that as our fraction. I'll write it as 6/10. That's how we say it, isn't it? And then since we know L is 7, unknown K, and then 6/10 I think even reduces, doesn't it reduce to 3/5? We hopefully can see you multiply by 1/7, and that finds us that K is 3/35. Our last one, those icky gross decimals, I'm going to take a quick second and do two things. First, I'm going to rewrite this in terms of fractions. Don't forget our fractions, 2/10. This is 2/100. So we have 2/100 times p minus, and then we have tens, hundreds, thousands, 10,000ths. So minus 2 10,000ths p squared. Going a little bit further, I'm going to factor out let's see, what should I factor out? Well, if I want it to match everything up here, I'm probably going to want a 1 to be the 1 minus something. So I think I'm going to have to factor out 2/100ths p. So I'll do this underneath just so it's a little bit more clear. So we're going to tackle that 2/100ths p, and we're going to take that from each one of these to do something minus something else. Well, 2/100ths p times 1 will give us that first term. But then the second term, we took out the 2, so that one's not bad. It's going to be a 1 up top. Instead of p squared, it'll be p. And then we have to think, well, 100 times what is 10,000? There are 2 extra zeros, so we need 1 followed by 2 extra zeros. Okay. From here, we can see our carrying capacity. L will be 100. And then our same game of this guy is both K and L multiplied together. So we can say K times L has to equal 2/100ths. We know, however, though, that L is 100. And so we have to divide by 1/100th to give us 2 10,000ths, or if you simplify, 1 5,000th. Alrighty. That, I would say, is probably the most work of anything we have to do. Let's take a look at the rest. Part 3. We do need to identify when P of t is growing the fastest. And remember, if we have logistic growth, where is the steepest part of the graph? Well, the steepest part of the graph is right in the middle. It's at our point of inflection. So that is because our second derivative, our inflection point, and we saw this on our sign chart earlier, is going to be the spot where the first derivative has a relative max. And if that has a relative max, a maximum first derivative is like a maximum slope. It's when the slope is the biggest, or when your equation is growing the fastest. So when they ask us to find where P of t is growing the fastest, what they really want is to know where is the inflection point. Now, our inflection point is always half of the carrying capacity. Remember, it's halfway through there. So I think we just need the carrying capacity, and then we can take half of that. Luckily, these 4 equations are the same as the ones we just did, so I'm going to start with the carrying capacity of each of these. Something like this. And then let's determine the value of P where the population is growing the fastest. So that's just going to be half of the carrying capacity, which is 6. Or I think mental math-wise, this shouldn't be too bad, right? And there we go. Pretty darn easy if you know what they're asking you. Okay, moving on. We also should be able to analyze the rate of change of a logistic growth function. In particular, we're going to need to take the derivative of the logistic growth function and create a sign chart to decide where the first derivative is increasing or decreasing. However, this is pretty darn easy because our sign chart's going to look the same every single time. So identify the intervals of P where the population is increasing. So increasing, right, means P prime, or dP dt, is positive at a decreasing rate. Well, the first derivative is always positive, so that's kind of out. We don't really care about that. But when is the first derivative increasing at a decreasing rate? What does that look like? Well, there's probably 3 ways you can think of an increasing rate, right? We could increase consistently, just a straight line moving up. That would be increasing at a constant rate. You can increase at an increasing rate, which means you're going up, but you're doing it faster and faster and faster. Or you could increase at a decreasing rate, which means you are moving up, but doing it slower and slower and slower. If you think about this in terms of concavity, concave down versus concave up. If we want to know where our function is increasing at a decreasing rate, and we're thinking about our logistic growth function, increasing at a decreasing rate is the second half of our logistic function. It is also where the second derivative is negative. Can we see that this portion of the graph is concave down? So how do we determine where the second derivative is negative? Well, that's not bad. It just occurs from the point of inflection to the carrying capacity. And so how do we state this? Well, we start with the point of inflection, right? We know the point of inflection is half the carrying capacity. Oh, and this one is a different one, isn't it? But the carrying capacity is just 1,000 here. So the point of inflection will occur when P is 500. The carrying capacity is 1,000, so therefore our equation P is increasing at a decreasing rate from 500 to 1,000. We're using open intervals here because we can't equal the carrying capacity, and we traditionally use open intervals for the second derivative. So here we go. It's going to be the same every time here, unless we were dealing with logistic decay. Logistic decay would be phrased differently because everything is decreasing. They might say decreasing at an increasing rate, and decreasing at an increasing rate is the opposite of what we're looking at from here. However, I think K is positive on all of these. I don't see any negative K values, so I think we're probably in the clear here, and we can do the same thing every time. So let's find our point of inflection. That's going to be half of the carrying capacity, which is 3. And so that tells us that our function is increasing at a decreasing rate from 3 to 6. Similar idea over here. Notice our carrying capacity. So our point of inflection, half the carrying capacity, which is 6. And so we're increasing at a decreasing rate from 6 to 12. One more. We saw this one earlier. I'm just going to cheat and peek back here. The carrying capacity is 100, right? So our point of inflection is half of 100, which is 50. And so from 50 to 100, we are increasing at a decreasing rate. What else do we need to do? Well, we only have 2 more main concepts. You should be comfortable creating a logistic differential equation from a word problem. You may have to solve for one of the variables first, typically K, the constant of proportionality. You've probably done that in science before too, right? They're like, if you're talking about growth rate or decay rate, you might have had to isolate K. Sometimes you have to use natural logs. It's very exciting. You don't have to do anything like that here. So let's take a look at an example. The number of students in a school who have heard a rumor, back to Umbrella Academy, at time t hours is modeled by the function P, the solution to a logistic differential equation. At noon, 50 of the school's 500 students have heard the rumor. Also at noon, so everything's taking place at exactly the same value of t, time, P is increasing at a rate of 20 students per hour. Write a logistic differential equation to model this scenario. Well, what did they tell us? I tried to highlight the important numbers, or the only numbers here. We know that P is increasing at a rate. P increasing, I think that's a derivative. In fact, I think we'd write that as dP dt. So we know that dP dt is 20 students per hour. When the population is what? Well, at this point, our population, our output, is 50. And you might be tempted to say, well, isn't the population 500? Well, this P doesn't mean the total population. This P just means the population who have heard a rumor. And so only 50 have heard the rumor at this point. However, where does the 500 come into play? Oh yeah, that's the carrying capacity, right? We're trying to reach 500, or we may reach 500 at some point, but that's what we're trying to model. So let's use our common differential logistic expression. We don't know K at this point, but we do know dP dt is 20. K is unknown. P we know. P is 50. And we know the carrying capacity is 500 minus 50, right? At a certain time, we know all of these values, which is going to allow us to solve for k. When we go through, 500 minus 50 is 450. 450 times 50 is 22,500 equals 20. Dividing off the 22,500 gives us our constant of proportionality, 1 over 1,125. Thus, our final logistic equation, or logistic differential equation, I guess, is 1 over 1125, that's k, times p, times 500 minus p. And now for any value of p, so for example, if we wanted to know how fast this rumor is spreading, we could pick a population number. Let's say, I don't know, maybe when 100 of the students have heard it. You plug in 100, do the math, and it'll tell you how fast the rumor is spreading. Right? I even know what the graph of this looks like in case you're curious, and I'm sure you are because you're watching this video. Carrying capacity is 500. The graph looks something like this. This will probably continue down here. Our point of inflection is at, of course, 250, half the carrying capacity. So I know that if the number of people that have heard the rumor is less than 250, our rate that the rumor is spreading is increasing, right? It's steep. But then after 250, the rate slows down, which makes sense in a situation because there's going to be fewer people that haven't heard it, and so maybe they're off campus at a time, whatnot. It takes a while for the last couple people to hear that rumor. All right, we really only have one more concept to run through, and then you guys get a few practice problems, and that's it for today. The last part is to find the limit of p of t, of the original logistic function, which again, you don't need to know, as t approaches infinity given an initial condition. This limit only has two options on what to approach, right? And I'm going to show you those two graphs over here really quickly, right? Either logistic growth looks like this, and so as we move along the t-axis out to infinity, what are the population values approaching? Oh yeah, they're approaching the carrying capacity. Or we might have an equation that shows logistic decay, and so as we move out to infinity, then we are approaching 0. That's it. Very, very straightforward here. So, let's see, the limit only has two options on what to approach, either the carrying capacity or 0. How do we know which one? Well, it's all about k. Remember that when k is positive, we show growth, that's our more common one, and when k is negative, we show decay. So, evaluate the limit as t approaches infinity of p of t for each logistic differential equation, then sketch a sample graph including the initial condition, inflection point, which may be off the graph, we'll talk about that, and carrying capacity. Now, I actually, in my solutions that are posted on Teams, I derived the actual original equation and graphed that. So my graphs on Teams are absolutely exactly what they should look like. Ours don't have to be perfect. You're never asked to draw something like this. I just think it's good practice to get a really full understanding of this problem. So let's rock and roll. We have this, and actually I'm going to try to acquire some information over on the side. We'll use this area here, and then I'm going to sketch a graph over here as well. Okay, so let's take a look at this first one. We know the carrying capacity is 12, which means that the point of inflection, and these are all p values, right? The point of inflection is half of that, which is 6. And we also know it has to contain the point 0, 3, and so I think we're pretty much ready. We have our 0. We know that our carrying capacity is at 12. K is positive. I don't see a negative number out there, so we know we're growing. We have to include the point 0, 3. And then if you think about the point of inflection, 6 is greater than 3, and since we're growing, that means my point of inflection is going to happen still somewhere up here. It doesn't have to be perfect. So I'm going to go here, there's my point of inflection, and we have our graph. And that's all we need. However, they did ask us to evaluate the limit as t approaches infinity. Once you see the graph, though, I think that shouldn't be too terrible. As we move infinitely far to the right, we approach the carrying capacity, which is 12. Okay, let's try another one. Same idea. Most of this is the same, too. Carrying capacity is still 12. Point of inflection is still 6. We still have the same initial condition. We're like, well, is this any different at all? Well, it is. There's a negative k, right? We see a negative value out front, which means this is going to be slightly different. Okay, slightly different. I'm going to kind of center this graph a little bit more here. We have the point 0, 3 still in the same spot. We have the same 0, the same 12 for our carrying capacity, but now my graph is going to go the other way. And so because 6 is bigger than this, it can't occur over here, right? It's got to occur somewhere up here. So my graph is going to look something like that. And so realistically, if you're only looking at a time from 0 to infinity, your graph wouldn't even look logistic. It would just look like some little decay graph. But nothing too bad. Doesn't matter how accurate you are there. We just need to get the general shape and realize that we approach 0. Let's try 2 more. Looking at these last 2, I seem to notice that both of these are positive values, so I think all of our growth graphs will look like the first one, which maybe is nice for you. And again, generally we only see logistic growth on the AP exam, but never a bad thing to examine decay as well. Let's work through. We know L, the carrying capacity, is 6. We know our point of inflection, half of 6, is 3. We have an initial condition, which is 0, 5. Okay, so we have a graph, looks something like this. Okay, 0, 5 is actually pretty far up because our carrying capacity is 6, isn't it? So carrying capacity, I guess I should follow the same colors there, is 6. The initial condition is 5, that's way up here. And because it's growth, I know we're going to do this. So what that really means is that this graph, and notice the point of inflection is at 3. 3 is right about here. So I'd say my point of inflection is way over here, and there's my point of inflection. That did not go the way I wanted. There we go. Something like this. So again, it'd be very weird if you only looked from 0 to infinity because you just see the upper part, but you get the idea. Our limit here, the same with any growth logistic model, is going to approach the carrying capacity of 6. In fact, we could probably even do that on our last one here. We see that our carrying capacity is 30, which means that our point of inflection is 15. Initial condition again of 0, 5. This time, though, we can find the limit ahead of time. We could have done this on each of them, and we'd realize, oh hey, this is growth, positive k value, so we're growing towards the carrying capacity. The carrying capacity is 30. Sketching the graph, though, just getting our last bit of practice in here. Okay. We know that this is 30 up here, and 0. 0, 5, that's pretty slim down here. Point of inflection is 15. 15's in between 5 and 30, so I think that's going to occur somewhere up here. And so we have our logistic growth function. So, as a final summary, what do you really need to know about logistic differential equations? The answer is not that much. You should be comfortable with the format of the equation and know what each of the variables mean. Remember, memorize this one, derive this one if you need it. You need to know when the population is growing the fastest, and that occurs at half the carrying capacity. You should also realize that that is your inflection point. POI, not ROI. What happens as time grows infinitely large? Well, you either approach the carrying capacity if you're growing, or you approach 0. I don't know why it says negative infinity, awkward. Or you approach 0 if you are decaying. Last but not least, much more uncommon, you do need to be able to find a variable if you're given all the other variables in here. And that's more uncommon because although there is a little calculus, realizing that you're going to replace the rate, there's not a lot of calculus there. That's more of an algebra skill. Okay, so the rest of this packet has a combination of multiple choice questions that I've taken from past exams, and then at the very end, the last 2 pages, I have 2 free responses. This one's from 2004, and this one's 2006. I haven't seen a full free response on logistic equations since 2006. That was actually the year I graduated high school. So that has been quite some time now. So I would not stress, but they can come up, right? They could totally give you a full free response on one of these. So work through. I have worked out all the solutions to each of these problems. If you have any questions, you can always ask. And as always, if I made mistakes, please let me know so I can go back through and fix them. Congratulations on getting to the end of AP Calculus BC, and I'm excited to jump into our review.